Hello, everybody. We chose to do our project on the vibratory effects in bridges, and this is by Ben Druin, Will Philpott, and Haley Evans. For an introduction, bridges are an integral part of everyday life. We each encounter them on a daily basis. To the untrained eye, they may seem fixed or unmoved, but in reality, there are small oscillations and vibrations within them that are necessary to ensure stability and safety in differing weather conditions. However, this must be monitored and controlled. Common ways of doing this are through elastic bearings and liquid column dampers. For some background information, it's necessary for bridges, like I said, to oscillate with wind and other weather conditions. Otherwise, there could be structural damage involved and the bridge could collapse. For resonant frequency is where something vibrates at the highest amplitude. And this is important for bridge construction because it is possible for bridge collapse to occur if the oscillation force from vehicles and weather combined will cause bridges to vibrate at that said frequency, which has happened in the past, as the photo on the previous slide depicted. And the longer the bridge, the lower its resonance frequency is.
A modification we looked at was elastic bearings, and they are a device used on bridge supports to isolate ground forces and vibrations from affecting the structure of the bridge. They're typically composed of alternating layers of steel and rubber, and this allows them to be very practical and economical, especially on long-standing bridges, as more of them are needed. They're designed so that they can press on vertical loads and allow for horizontal rotation, as seen in the figure on the right. The downside to these bearings is that they prevent vehicle-induced vibrations from dissipating through the supports into the ground. A study that we looked at in Taiwan looked at 2 bridges and tested them to see what the effects were. They originally assumed the bridges were simply supported, and the math that they used to calculate what would occur is represented by the dotted line. And the results they actually got are shown with the solid lines. And both the math and the test found that the bridges have a resonance speed of about 60 kilometers per hour, as seen by the peaks on the chart. The amplitudes, however, are very different, which leads to the conclusion that the elastic bearings drastically increase the amplitudes, resulting in larger accelerations.
The other type of modification we researched is liquid column dampers. Liquid column dampers are installed on the cross section of the bridge to isolate pedestrian-induced vibrations. They're best used when lateral, horizontal, and torsional motions are dominant. The image below, you can see the structure of the damper. The basic idea is that since it's a sealed tube liquid column damper and the gas spring effect must be taken into account, the damper is ideal for damping the vibrations in low frequency bands up to about 5 Hertz. This type of damper is effective in pedestrian, group walking, or running events. In a group running event, the vibration effects are much higher and could cause damage, but with this type of damper, it does not. It's also effective in gusty wind situations and very effective in other type of weather-related settings. The image below shows tests done both with and without a tuned liquid column damper, also known as a TLCD. And you can see that based on the lines that with the tuned liquid column damper, the vibration effects are much more minimalized.
Monitoring the structural health of the bridges is essential in ensuring that bridges are safe over time and aren't deteriorating. And with this in mind, you obviously need energy to run the devices that are doing this monitoring. Renewable energy is the most ideal energy for these systems, as wires aren't necessary and batteries require replacements that can be expensive over time. With the knowledge that there is already kinetic energy generated as bridges vibrate due to vehicles or wind, the goal of designing a vibration harvester that was capable of turning these vibrations into energy and power was set. In turn, inertial power generators were modified, allowing a bridge's structural health to be monitored basically on its own power. And it was found that the ideal maximum power that can be generated from these generators is given in the formula on the right, and the graph below it just visually shows the power that can be generated based on the bridge's vibrations. Physically, these devices are housed in an aluminum case, and inside There's an inertial mass in the middle of two electromagnetic frequency induced generators. And as the inertial mass moves, it pulls a spring along until a force imbalance on the system causes the two to separate. The free generator then resonates at its high natural frequency, which converts the stored mechanical energy in the spring into electrical energy. And mathematically, these systems can be modeled as three mass spring damper systems that influence each other through magnetic latching systems. And you can see that in the bottom right figure.
To recap, in this presentation, we went over resonance frequency, two types of modifications being elastic bearings and liquid column dampers, and monitoring of bridge systems. Thank you for watching and have a great day.